Okay, folks, sorry about all the confusion this week with the snow, and we had a non-fatal medical emergency in the family. Everybody's fine, um, but sorry for the disturbance. Anyway, let's get going on this week. I just want to review very quickly what what decision trees do and why they're fundamentally different. So up to this point, we've been looking at regression models and seeing how we can extend those. The second big category of machine learning models we'll study in the program are decision trees and ensembles or sets of decision trees. And the third being then deep learning in 703, in Mod 7. So let me set it up this way. Here's a regression problem, happens to be quadratic. You can read about the details, but basically you have a feature and a prediction, okay? And based on whatever this is, you can read about it. What's the simplest thing you could do? The dumbest, simplest thing you could do to predict housing prices based on this x-axis. The simplest thing is to take the mean, take the average of all of these values, of all of these y values. It would be somewhere like here, right? And for every one of these x values, you just say the mean. It's not a completely stupid idea. At least you get the range, you sort of, right? But it's not very accurate, obviously. Okay. What if we split this in half? Let's say we split it at 15. Now we take this set and we take this set, split the samples in half, or not half, but partition them into two groups, some less than 15, greater than or equal to 15. Now take the mean of each one of those. Well, then the mean on this side is going to be a little bit higher. The mean on this side is going to be a little lower. Okay, that's a little more accurate. If you calculate the mean square error against these predictions, these stupid, trivial predictions, you're going to get a line straight across here. You're going to get a line straight across here. And you can calculate the mean square error. The mean square error over the entire prediction process, over this model, is now better. Okay, keep doing it. Keep splitting. Split, say, on every 5, 10, now the mean here is going to be up here. The mean in this range is going to be somewhere around here. The mean up here is going to be somewhere around, it's going to be better. It'll be closer. And the cumulative, the average squared error, the mean square error over the entire set is going to be better. In the end result of this process would be each separate sample, okay, would, if there's only one, then the mean of that, the average, remember what you're doing is take the average over the sets as the prediction, would be perfectly correct. So that's what a decision tree does. What the decision tree does, okay, let's go back to here. It takes you start with all of the samples. That's the parent, the top, the root of the tree, and you split it into two pieces based on some threshold in the feature. And then you take the mean square error of the left side and the mean square error of the right side, and then you average them. You're just taking the mean square error over the entire, all of predictions now. For classification trees, it's a little different, okay? But what you're going to end up with is, if you keep doing this, you start with everything, you split it somewhere which optimizes the reduction in the mean square error. In other words, you're making a more accurate prediction by splitting this somewhere into two sets. Now, what the decision tree will do is try every possible split. And there's optimizations we don't need to go into, but basically we'll try to find a place in here where it can make the split, where when you now have a prediction, remember that in the end, whatever prediction you have, whatever nodes you have at the bottom of the tree, because you're going to keep splitting this apart until you have these little subsets, right? That those predictions are as accurate as possible. So at each point, you're going to split and try to reduce the mean square error. You can't just say, it's got to be a 15 or 2. Somewhere in here, there's going to be a split, which reduces it. And so essentially, you're just creating predictions based on the average for the set that remains. So here, this is the entire set of all. Each node is a set of the samples. So here you have the entire set of samples for housing prices, Boston housing prices. You split it. This is LSAT based on if it's less than or equal to 9.725. Okay? Then if it's less than, it goes this way. If it's greater than, it goes this way. Then you do it again. Then you do it again. Then you do it again. Now, let's just focus on one feature. What's going to happen then, if you do it with one feature, eventually you'll get to the point where you've made it as accurate as possible. However, you can overfit. If you make it too small, then each prediction is just the point. You've memorized the data set. Again, not a great idea. You want this to be able to generalize, right? Not just memorize. So you can't just grow the tree down as big as possible, because then you're splitting on each separate data item. You just memorized the data set. It's overfitting. So you want it to generalize, right? So there are various criteria. How deep do you go? How many nodes, when you split, can you split down to one? Generally doesn't make a lot of sense. You want how big are the sets? Is there a limit on the size of the sets? We'll talk about that in a moment. But there's a lot of different hyperparameters you can set. So the other thing is that we just looked at one predictor, right? We only looked at one feature. So you can also try different features. So in a multi-dimensional set where many features, right, you can iterate through every possible feature and every possible split. But then again, there are optimizations here because you're dealing with floating point numbers. But find the split which reduces the mean square error, given that when you end up with leaf nodes that don't get split any further, what you're going to do, the prediction is going to be the average of the y values, okay, of the target. So here we've split on LSAT. Then when it comes down here, it turns out DIS, distance, I think from something or other, you split on distance. Here you continue to split on LSAT. Then here we stopped. We limited the depth here to 3. There are various criteria. You don't want to go all the way down and split to individual elements, because then you're memorizing the data. So where do you stop to get the model which generalizes the best based on the validation score? Use the same idea that we did before, right? Training set, validation. So we have a lot of hyperparameters which we can use to create these sets. Now let's go to the homework, okay? And let me just go down to the bottom and show you. First of all, I went through, this is maybe a little late, but better late than never, because I wanted to make the point about which one, which one do you want to think about? Root, mean square error, mean square error. Remember, mean square error has the wrong units. It's generally best to use the same units as the problem when you're trying to understand it. And root mean square error takes the square root of the squared errors, mean squared. We're going to use mean absolute error. That often works a little better for reasons which are described here. Generally, outliers are not punished as much. But Appendix 2 has a description of all the decision tree hyperparameters. I call them parameters here. And there's a large number of them. Okay. So for example, the criterion is what's used when you do that split and you take the mean at the leaves of the tree as predictions. What's your error measure? Squared error is the default. If you're doing classification, use something called Gini impurity. The default is squared error. You have a bunch of different hyperparameters. Look at these. So, for example, here, min impurity decrease. You only split it if you get a certain amount of improvement. It's kind of like the, waiting, if you're not getting enough of an improvement in the validation, then you could stop. This alpha is a complexity parameter that allows you to construct a tree and then prune it. And we talk about this in the lesson. What's the minimum number of samples you can have in a leaf? The default is 1, but maybe you want to say, look, to prevent overfitting, I want to make sure that, have at least 10 when you have a big set. Splitter, which strategy is used, you can read about these, but we're going to focus on these 4, which seem to have the most effect. What's the maximum depth you allow the tree to get to? No path in the tree can be longer than that. When you say none, there's no limit. It'll go as far as possible. Generally, none means it might overfit unless you have some other way of controlling. Maximum number of leaf nodes. So as the tree grows down, the width of the tree at the bottom, how large do you let that get? So max depth and maximum leaf nodes in some sense control how big the tree gets. When the split happens, I left this out detail in the description. You don't necessarily look at every feature when you try to figure out the split. If you set this to none, all of these defaults are none, no limitations whatsoever. It will look at all the features every time and find the best one. If you set it to some number here, okay, and the limit, of course, would be the number of features in your data set, then it's going to randomly choose that number. If you set it to 10 and you have 15 features, it will randomly select 10 and just examine those. There's an efficiency consideration here, but there's also an interesting thing that happens. Sometimes adding randomness will improve results. It's true throughout science, audio, in machine learning. Sometimes additional randomness actually helps. It distributes the information out in a useful way. And so you can actually, create a tree that will generalize better if you don't look at every feature every time, but it will randomly choose them. Okay. Then what's the minimum number of samples before you split? And so these are the ones that seem to have the most impact. So what I want to do is go through and just talk about a strategy here, a workflow for how to look for the ideal sets of hyperparameters. We're going to look at those 4 settings, okay? If you leave them all at the default, it will do the maximum amount. It will make a tree as big as possible. It will split it to as far as possible, and it will have no restrictions whatsoever. Generally, this is a bad idea. Generally, it will overfit when you do this. So you don't want to do that. So what we're going to do, we're going to look for, of course, we're going to look for the minimum validation, cross-validation score based on the MAE, okay, the mean absolute error. So if you plot that against one parameter choice, say here, let's make this a little bigger. I think these are the ones that we'll see later. Against the number of estimators, say, there's going to be a point where, you know, as you increase it, you're going to get improvement. And remember, you're looking for the smallest MAE. But here, if this were the only parameter, then you'd say, well, maybe here, you know, here, probably here is the minimum. But that's not what's happening. You have multiple parameters. You're going to have 4 parameters. So, and when we get to the next week, there's even more. And then in deep learning, there's even more. So this will not be in isolation. If I look at, this is actually for next week, but the point is the number of estimated number of trees for bagging. But if you, if now we get a shape like this, you could say, well, that is pretty definitive. What's going to happen if I change a whole bunch of other parameters? Maybe it radically changes this shape as well. But we'll make an assumption, a simplifying assumption here, that probably you're not, you know, that the hyperparameters, with some exceptions, are going to affect each other, but not radically. And so you might say to yourself, okay, probably the ideal here is somewhere around here. I don't have to check this range. I don't have to check over here. I can isolate it here. In this case, you couldn't do that. This could change. You know, they're pretty close. In this one, you get different shapes, right? And you have to interpret them. So in this one, it's pretty clear that when you know, this one is going to stabilize at some point, and you're not going to get much improvement here. So in this case, you know, you can probably set it right here, or simply, maybe in this case, none would work because you're not going to get much improvement, right? So what we're going to do is look at the curves, okay, and we're going to try to figure out for each one of these parameters in turn, we're going to try, for example, in the first case, max depth and max leaf nodes kind of do the same thing, because with a binary tree, you know, you don't have infinite width, or you don't have arbitrary width. It has to split by 2. So there's a strong relationship between the depth and the maximum number of leaf nodes, although it's not a perfect triangle, right? So we'll do those together. And then we'll look at max features, how many features are chosen randomly. And then we'll also look at min sample split. In a sense, the intuition is lost once you start doing this. It almost doesn't matter what they are. You're just trying to get the shapes to look right. So we're gonna think about these. And then we're going to introduce a radically new idea, simple idea, but something you haven't seen before. And that is, we'll do exhaustive search called grid search. And what you will do is, remember, what we are looking for are the optimal settings for each of these 4 parameters. And so we're searching the space, a 4-dimensional space of settings, including none, or ranges, you know, or values. and we're looking for the optimal settings. One way to do it is to simply search exhaustively. Now, if you do that for big ranges, it will take freaking forever. I've done this. I've tried this. As I often say, I can save you time. I've made every possible mistake, or at least I've tried every possibility. If you set the grid, if you use grid search, remember, it's going to run the problem for every single point in that four-dimensional space that you're searching. It'll take forever. So you have to restrict it. It can be useful to do exhaustive search over a small range. Next week, we'll start to look at, and I'll show you down below, we can do random search. And that often is a good proxy for what you'll find with grid search. So I do want to make the point here that there's another skill we're talking about here. Everything you need is in the coding notebook. Go look at if you haven't looked at it, go look at the coding video. Save you a lot of time. And grab the code for that. The link is right there. And use that code. Cut and paste, change it, think about it. It's an essential skill. There are many places in machine learning, especially in machine learning, and especially, I would say, in deep learning, where people just, there's just lots of template code and people adapt it and use it. And it's not regarded as plagiarism unless you claim that you're not doing it. But you use code, change it, move a few things around, and so go to that notebook and use it. Okay, so we'll again use 5 repetitions, 5 folds for repeated scoring. We'll use mean absolute error. I said change from our previous coding examples. In the coding video, I did mean square error. Last week, we did do mean absolute error. So it's the same data set. Okay, load it, blah, blah, blah. I give you the same. I give you a function called run decision tree regressor, and you give it the training set, okay? And you set all these criteria, okay? And it's going to build a decision tree based on your settings, based on the training set. So remember the pattern here is you give it the training set, it builds the model. In this case, it's not just a simple formula like you use with linear regression. It has to actually go through and create it, maybe randomly choosing features. So it may take a little time, not that long. But anyway, you can set all of these features. We're only going to play around with 4 of them, as I said. Then, having built the model, having fit the model, okay, to the data, you're going to now take the cross-validation score. It's going to go through and do cross-validation, the partition into 5. And we're going to use negative mean absolute error. You know how to do this. You take the negative here. And now we have, for this particular setting that we used here, whatever the settings are, okay, I put these all at the default, so you can be assured that these are the default. It will now return that value. And it will return it. Okay, so this is your harness, I guess, for doing these experiments. And here's the repeated CV, blah, blah, blah. Okay. So the first thing to do is to try max depth, max leaf nodes. Baseline, try that. And then which depth, max depth, produces the lowest MAE? Well, you're going to have to try a bunch of them. And you're going to put it in a loop, like we did in the coding video, and see what happens, okay? And use the code from there. So you can do that. And the first part is, how does the baseline model work? Okay, just try it. And so here, show you how it works, right? No, you're using the defaults. Don't have to do anything else. Just give it X train, Y train, baseline score. Here it is. Going to print it out with, in nice human readable form. I encourage you to do things like this, right? So you don't have to copy. That's why I say use an expression. Okay, now, when we explore a number of possibilities here, now we have to do something a little different. I showed you how to do it in the coding notebook. And what we're going to end up with, we're going to put it in a loop. I tend to use this TQDM. It shows you a progress bar. Do what you want. But here, you see the parameter list here. I'm going to try values from 2 to 49, right? The 50 is the upper bound, in units of 1. If I had put 5 in here, or say 2, it would have done 2, 4, right? But here I'm going to do individual. And then for the depth in that list, run it, collect together a bunch of them, okay, and then plot them straight out of the notebook. And then you find the minimum. Okay, so here's what we end up with. It overfits if you let it grow as deep as possible. Okay? And make sure you understand that overfitting would be, just going and memorizing the data. And it doesn't, when it's too big, it flatlines at a not very good value. The best value, which is 23,000, blah, 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 was found here at 7. So limiting the depth of the tree to 7, okay, gives you the best result. So put that in, okay. Then we're going to try maximum number of leaf nodes. Now, it's sort of interesting to think if it was depth of 7, each unit doubles, right? So you can get 2 to the 7. It's going to be somewhere around here, right? So here, 95, limiting the width of the tree at the bottom to 95 gives you the best result. Okay, then we're going to run this. So is there a combination of these two parameters that yields a better score? Okay, so now you can try, see if you can hone in by setting one or the other, and see if you can go into, here I set this to be one of them, and I tried the other one, okay, and okay, then I end up here at 12. So given that I have set this to 95, now at 12, you can set both of them. So another way you could do this is have a double for loop. We're going to essentially do that later when we do grid search, but one could do that. Here I just tried one of them, tried the other one. You could reverse it, try it the other way. Explore. They don't take that long to run. I mean, it ran in 31, on my machine, it took 31 seconds, however many it did, 48 different examples, so less than a second for each one. So, think about how you might do that in a little better way. Okay, so now we'll try max features, okay? Use, again, iterative, use the best model you got in problem 1. Now add one more. Of course, you should be thinking right away, how do I know that that when I change max features, it doesn't change the result of the first experiment? Of course. But we need a systematic way to go through and try this. We are exploring these features. In the end, you will probably use an automated way of doing this, like grid search or randomized search. But you need to understand how this works. So again, we'll experiment given the values I had above, that for the 2 of them, whatever it was. Now I try max features. I forget how many features there are in the data set, but here 60, which is, I guess there was 73. Pretty close to the maximum number. In this case, you might say none is maybe a good choice. I mean, can you really distinguish here, among these. You could say 60, okay. But in the end, you might say, it's so close to the top. This is the hard stop. You can't have more than 73, so maybe none is a good choice. Here, I did say none. And then min sample split, okay? So let's try that. Again, we choose the best values. Minimum number of samples before you split. It needs to have at least 20, okay? Or 22. So at this point, you sort of lose the intuition of what you're looking for. It's important to maybe understand that certain of them are automatically going to, not automatic, but naturally going to be related. And so that's why we did the first two, sort of the size and shape of the tree. Here we're delving into how it does the splits. One could, of course, go through and try all the other hyperparameters. We're just looking at these four. Okay, now, for this last problem, the second to last problem, we're going to use grid search. So the idea here is that, and I showed you how to do this in the coding notebook, you set up what's called a parameter grid, and this is a dictionary, and you can give it a list, okay? And you can see here I've used some ranges, okay? You can have an explicit list. Basically, you need to give it a list, and the range is turned into a list. You can use any number of these. And when you do this, okay, when you do grid search, okay, it's going to set up 5 for loops. Okay, for these, it's not going to do much. But what you're going to get out of this, okay, is an exhaustive search over every possibility. It's going to take 4 freaking ever if you make the ranges too big. So that's the point of going in here and saying, I'm going to restrict this range. I'm interested in the range. Remember max leaf nodes, it was 95 here. I don't know, I tried none here. I'm not sure if that's the best way to do it. You might want to set a range here. Probably better here to set a range around. I don't know why I did none. Max features, again, I put none here. I think I was just experimenting. This is not the best solution necessarily, min sample split. But for your analysis of these, hone in on it, okay? And you can naturally just multiply the sizes of all of these, and you're going to see how many experiments it needs to run. Now, it's probably less than a second to do each experiment, but still, if you have 1,000 of these, if by the time you multiply the size of all these, you can have a single one like this. But a range, of course, it's going to go through every possible one. You could set, an increment here. Lots of possibilities, but just remember that when you do this, it's going to go through every possibility. A very useful thing. So this is how you hone in on it. And what it will do, depending on how you set it, somewhere you can tell it how many, right here. You can set how many you want to see. It'll give you the top 10 results in terms of the mean square error. So, I mean the test score. So mean absolute error. And here's the best possible setting. Here's the best result you can get. Max depth, none. Max features, none. Max leaf nodes, 99. Min sample split, 33. But it's important to realize, if you look at this, look how close these are. When you're getting down into the 5th significant digit, it's probably not that relevant. So these are pretty close, right? Even down here, the 10th one, 841, 863. These are all pretty close. Okay, remember that you're doing this, it's a very strong paradigm looking for the minimum validation score, but it's not a guarantee. So you can't make these fine distinctions. So yeah, but we'll choose the top one. And so this gives you a sense for how to build an optimal tree. Okay, then what you're going to do is final exam. You're done building the tree. Let's check and see how we did. You're going to take the final values. Did I put them in here right? Maybe I didn't. 99, 33. I didn't put them in here properly. But you put those values in here. Do it exactly whatever the best result was. I didn't do it right here. And fit it, do the prediction, get the mean absolute error, and that's your test score. Oh, it didn't get printed out with a $sign. Don't worry about it. Oh, it did it down here. Yeah. Okay, so that's the assignment. It's a workflow. It's in a sense of prototyping, right? You're trying different examples, and you're trying to find the range where you think the optimal value lives, and then you will exhaustively search. Now, exhaustive search is in some sense a little silly if take this with a grain of salt, as they say, that you're going to get answers which are very close within some range. But the spirit of this is to find the absolute best one, right, using this grid search. And it's a very useful paradigm. People use it all the time, and it's worth getting used to. Now, for next week, looking ahead, you're going to use randomized search. And don't do it for this time, but I just wanted to put it here to show you where we're going. Randomized search, you're going to give it either a list, okay, and it will choose randomly from that list, or you're going to give it a generator, which is going to randomly generate integers from 4 up to 20. Yeah, should have been 20. And this will generate a random number in this range. So you still have the ranges, except now it chooses a random number. So instead of searching exhaustively, it just randomly picks points. And you can tell it how many to do, how many iterations to take. Otherwise, it will do the same thing. It will give you the best results. And you can tune, this is a very useful paradigm, because now you can basically explore the space. How much time do you have to search? Well, just see what 50 takes a second and a half, or say 30 seconds. Okay, I'll make it 500 and see what you get. Now, of course, it's silly to do it if you only have 100 different parameter settings to try. Randomized search may not be that useful, but you can try randomized search with larger ranges. And so that's another way of trying to hone in on the optimal settings. There is another paradigm, of course, which is to do some kind of search through the space. If you can imagine starting someplace random and just permuting one of them, see if you can improve it, keep moving around in this multi-dimensional space. Well, in this case, 4 different parameter settings. Choose a setting, permute them, and see if you can improve it, and just sort of search through 4-dimensional space looking for the best result. That's another paradigm that's used by various programs for creating models. We're not going to do that right now. Anyway, let me stop here. Good luck. This is exciting stuff. The state of the art is, in most cases, Kaggle competitions and so forth are won by, for regression at least, are won by some sort of decision tree model, usually in ensembles, which we'll do next week. Okay, good luck.